So, here's something worth thinking about before you let your eyes close tonight. Right now, in this room, in the dark, in the quiet, your body is having a conversation with the universe that you have absolutely no awareness of. The atoms in your pillow are vibrating. The photons your eyes would catch if the lights were on are, even now, being absorbed and released by the molecules in the air around you. And somewhere in your body, at this exact moment, a handful of potassium atoms are undergoing radioactive decay, spitting out particles that pass through you and vanish into the night, all without your permission, all without your notice. None of this is happening the way you'd expect it to. Not in the smooth, predictable way that a dropped ball falls or a wave rolls onto a beach. It's happening in fits and starts, in probabilities and possibilities, governed by a set of rules so strange that for the first 3 decades after they were discovered, the very physicists who found them weren't sure they believed their own equations. That's quantum physics. And tonight, in the year 2026, it's more confusing than it's ever been, not because the physics changed, but because the world talking about it has gotten so loud. You've probably scrolled past headlines about quantum computers, breaking encryption, quantum sensors detecting submarines, quantum this and quantum that, half of it accurate, half of it marketing, almost all of it presented as if you should already understand what any of it means. You don't have to understand it right now. That's the whole point of tonight. We're going to walk through this slowly, gently, the way you'd walk through a house at night without turning on the lights, feeling your way from one idea to the next. If you fall asleep before we get to the end, that's not a failure. That's actually kind of perfect because some of what we're about to talk about only makes emotional sense when your mind is loose enough to stop demanding that everything behave the way common sense says it should. Because here is the first thing you need to accept, and it's going to come up again and again tonight in a dozen different disguises. The universe, at its smallest scales, does not care what feels intuitive to a species of mammals that evolved to throw spears and avoid lions. We built our intuition to handle rocks, rivers, and other animals. We did not build it to handle electrons. And so, when physicists went looking at the tiniest pieces of reality, they found something that broke almost every assumption they'd ever made, and it took them the better part of a century to even describe what they were seeing, let alone explain it. Let's set the scene, because context matters here. This isn't a story that starts in a shiny modern laboratory with humming supercomputers. It starts in dim gaslit rooms, with men in wool suits arguing over chalkboards, decades before anyone had heard the word computer at all. And it starts, oddly enough, not with something exotic, but with something as mundane as a piece of metal getting hot. Picture a blacksmith's forge. As the metal heats up, it starts to glow. First a dull, brooding red, then orange, then, if it gets hot enough, a blinding white. You've probably seen a stove burner do something similar, or watched a candle flame shift color near its base. This everyday phenomenon, an object glowing differently depending on how hot it is called thermal radiation. And by the end of the 1800s, physicists thought they understood it completely. They had measured it precisely. They had equations for it. They believed, with real confidence, that physics itself was basically a finished project. A famous sentiment floating around at the time, attributed to more than one prominent scientist, was that all the big questions had already been answered, and all that remained was to calculate a few more decimal places. That confidence was about to be humiliated in a spectacular way. Because when physicists took their beautiful, well-tested equations and tried to predict exactly how much energy a hot object should radiate at every possible frequency of light, something absurd happened. The math didn't just get a little bit wrong. It went completely insane. It predicted that any warm object, your coffee mug, your own body, a glowing ember, should be blasting out an infinite amount of energy at higher and higher frequencies, climbing without limit into the ultraviolet and beyond, which is, obviously, not what happens. If it were true, every warm object on Earth would be a lethal radiation source, and none of us would exist to notice. Physicists gave this glaring contradiction a suitably dramatic nickname, and that contradiction sat there, unresolved, embarrassing, and quietly enormous, right at the foundation of a science that thought it had already won. Nobody wanted to touch it. Nobody had a fix. It was the kind of problem serious, respectable physicists tended to politely ignore, hoping someone else would eventually clean it up. But one man couldn't ignore it. He was cautious. He was traditional. He was, by his own description, about the least revolutionary person you could imagine. A man who loved order and hated speculation. And in trying to patch this one small, stubborn hole in an otherwise perfect theory, he was about to accidentally light a fuse that would take physics apart and rebuild it from the ground up. A fuse that, once lit, could never be put out again, and whose full explosion wouldn't finish detonating for another 25 years. We'll meet him properly very soon. But first, it's worth pausing here in the dark just for a moment and letting that image settle. A confident science, sure it had won. A tiny, embarrassing crack nobody wanted to look at too closely. And one quiet, careful man about to stumble into the strangest discovery in the history of human thought without even meaning to. Let's stay in the present for just a little longer before we travel backward, because understanding why 2026 feels like such a confusing year for quantum physics is worth sitting with. If you've spent any time online recently, you've probably seen the word quantum attached to things that have almost nothing to do with actual quantum mechanics. Quantum healing crystals, quantum manifestation courses, supplements promising to align your cells with quantum energy fields, whatever that's supposed to mean. This isn't new, exactly, but it's gotten louder and it's gotten more convincing sounding, because real quantum technology has also gotten louder at the exact same time, and the two have started to blur together in a way that makes it genuinely hard to tell fact from fiction if you're not paying close attention. Because here's the thing, some of the wild-sounding quantum headlines from the last couple of years are actually true. In December 2024, Google's quantum chip, called Willow, ran a benchmark calculation in under 5 minutes that Google claimed would take one of the fastest classical supercomputers on Earth, something like 10 septillion years. That's a number so large it doesn't mean anything intuitively. It's roughly the age of the universe, repeated hundreds of trillions of times over. That claim generated real debate among physicists over exactly what it does and doesn't prove. But the underlying chip, the underlying error correction breakthrough behind it, was genuinely real, peer-reviewed, published in Nature. Around the same period, companies like IBM, IonQ, and a handful of Chinese research labs were racing to push qubit counts and error rates in directions that would have sounded like pure science fiction just 15 years earlier. So, When you scroll past a headline in 2026 claiming some new quantum breakthrough, it's genuinely difficult to know whether you're looking at a legitimate leap forward in human understanding or a marketing team borrowing the mystique of a subject. Most people don't fully understand to sell something that has nothing to do with physics at all. And that confusion is, in a strange way, the whole reason we're here tonight. Because underneath all of that noise, underneath the hype and the misuse and the genuine breakthroughs sitting shoulder to shoulder in the same newsfeed, there's an actual, coherent, beautiful body of knowledge, a set of rules discovered piece by piece over more than 100 years. That turns out to be one of the most rigorously tested, most successful theories human beings have ever built. It's not mystical. It's not vague. It's precise almost beyond imagination, and yet it describes a universe stranger than anything a mystic ever dreamed up. Tonight, we're going to try something a little unusual. We're not going to start with the confusing headlines of 2026 and try to untangle them one by one, because honestly, that would keep both of us awake far longer than either of us wants. Instead, we're going to do something slower and, I think, more satisfying. We're going to go all the way back to where this entire strange story began, more than 125 years ago, and walk forward through it, one discovery at a time, the same way the physicists themselves experienced it. Confused, unwilling to believe what they were seeing, forced by the evidence to accept it anyway. Because if you understand how we got here, the confusing quantum landscape of 2026 stops feeling like noise. It starts feeling like the latest chapter in a story you already know the shape of. You'll be able to hear a headline about quantum encryption or a wellness influencer talking about quantum energy, and something in you will just quietly know which one is standing on real ground. There's another reason to take this slow tour through the past instead of jumping straight into the present. The ideas that built quantum mechanics weren't handed down all at once, neatly explained. They were fought over, doubted, argued about at dinner tables and conference breakfasts, abandoned and rediscovered, sometimes by people who didn't believe their own results. The confusion isn't a modern problem. It's baked into the subject from the very beginning. Even the physicists who invented these ideas spent years insisting they must be wrong, must be some kind of mathematical trick, must eventually be replaced by something more sensible. Understanding that history is, in a strange way, the fastest way to feel comfortable with the confusion instead of intimidated by it. So, let's ease into it gently. Somewhere around 130 years ago, in a world lit by gas lamps and candles, a small group of physicists were sitting on top of what they believed was a nearly complete picture of reality. Newton had explained motion and gravity. Maxwell had unified electricity and magnetism into a single, gorgeous set of equations. Thermodynamics, the physics of heat and energy, felt buttoned up and understood. There was a real, documented sense of intellectual smugness in the air. A feeling that the great questions of physics had basically all been answered. And what remained was just cleanup work, refining numbers to a few more decimal places. It's almost comforting, in a way, to know that even the smartest people of their era can be that confidently, spectacularly wrong about how close to finished they really are, because buried inside their otherwise beautiful, working theories was one small, persistent embarrassment, a tiny mismatch between what the math predicted and what experiments actually showed. something to do again, with nothing more exotic than heat and glowing metal, and it was about to grow from a footnote into an earthquake, one that no one in that confident, candlelit era saw coming at all. Before we go back and meet the man who lit that fuse, it's worth pausing on a question you might be quietly asking yourself right now, somewhere in the back of your tired mind. Why does any of this actually matter to you? You're not a physicist. You're lying in bed. You have a job tomorrow, or a family to take care of, or simply a life that has nothing to do with electrons and photons and equations from 100 years ago. So why spend 2 hours of your night on this? Here's the honest answer. You are already living inside the consequences of everything we're about to talk about. Not metaphorically, literally, physically, right now. The phone charging somewhere near your bed runs on a processor built from billions of microscopic switches, each one relying directly on quantum rules to decide whether electricity flows or doesn't. Not inspired by quantum physics, not based loosely on quantum ideas, actually physically dependent on quantum mechanics being true every single time you unlock your screen. If quantum physics turned out to be wrong tomorrow, your phone wouldn't work strangely. It simply wouldn't work at all. The GPS signal that helped you find your way somewhere today, whether you were driving, walking, or just glancing at a delivery map, relies on satellites carrying atomic clocks precise enough to notice tiny quantum mechanical vibrations inside individual atoms. Those same satellites also have to correct for effects predicted by Einstein's theory of relativity, because time itself ticks slightly differently up in orbit than it does down here. Without factoring in both quantum precision and relativistic correction, your GPS position would drift by kilometers within a single day. You'd end up on the wrong street, the wrong side of town, within hours. If you've ever had an MRI scan, doctors were quite literally using quantum mechanical properties of the hydrogen atoms inside your own body, nudging the tiny magnetic behavior of your protons with radio waves, and measuring how they snap back into alignment to build a picture of your insides without cutting you open. The light from LED bulbs in your house, the lasers reading barcodes at the grocery store, the fiber optic cables carrying the internet into your home. Every one of these technologies exists because someone, at some point, took quantum mechanics seriously enough to build something out of it. So this isn't abstract trivia floating somewhere far away from your actual life. It's the invisible operating system running underneath almost everything modern about your existence. And that's exactly why the confusion around it in 2026 matters. When people talk about quantum computers threatening to break the encryption protecting your bank account, or quantum sensors that might someday detect things we currently consider undetectable, they're not talking about science fiction. They're talking about the next chapter of a story that's already been rewriting your daily life quietly for decades, without asking your permission or waiting for your understanding. And here's something that tends to surprise people the first time they really sit with it. The strangeness we're about to explore together tonight isn't some rare exotic behavior that only shows up in specialized laboratory conditions. It is happening inside every atom of your body, every second, all the time. The very fact that your body holds together, that your hand doesn't simply pass through the mattress beneath you, comes down to quantum mechanical rules about how electrons are allowed to arrange themselves around atomic nuclei. Solid matter is only solid because of quantum physics, Without it, there is no solid at all, just a universe of collapsing points with nothing stopping them from occupying the exact same space. So when we go back in time in just a moment to the confident, candlelit world of the late 1800s, keep this in the back of your mind. The strange discoveries those physicists were about to stumble into weren't a detour away from the real world. They were the discovery of the actual, literal foundation the real world sits on top of. Every technology built afterward, every phone screen, every laser, every satellite correction, was simply humanity slowly learning to work with rules that had been running the universe the entire time, whether anyone understood them or not. That's part of why the confusion in 2026 feels different from ordinary scientific confusion about, say, a distant galaxy or a rare particle collision deep underground. This confusion touches your pocket. It touches your health. It touches the way information moves around the entire planet in real time. Getting even a little bit clearer on how quantum physics actually works isn't just intellectually satisfying. It's a small piece of understanding the actual machinery running underneath modern life. Which brings us back to where we left off. A group of physicists in the 1890s, utterly confident their work was nearly finished, staring at a small, stubborn mismatch between elegant equations and stubborn experimental results. A mismatch involving nothing more exotic than a piece of hot metal glowing in a forge. They didn't know it yet, but they were standing at the very beginning of the chain of discoveries that would eventually put a supercomputer in your pocket and let satellites correct for the bending of time itself. Let's go meet the man who first noticed the crack in that foundation, because he really didn't want the job. So let's go there properly now. Not just the mood of the era, but the actual man standing in the middle of it, because his story is stranger and more human than most people ever learn. His name was Max Planck, and if you had to imagine the last person on Earth likely to overthrow physics as we knew it, you might have picked him. Born in 1858 in the German city of Kiel, Planck came from a long line of academics, lawyers, and theologians, a family that valued order, tradition, and careful, respectable thinking above almost everything else. And Planck himself absorbed every bit of that temperament. He was methodical. He was formal. He loved thermodynamics specifically because it felt settled, dependable, almost architecturally complete, the kind of subject where the rules didn't shift under you. In fact, there's a story, well documented, that when Planck was a young man deciding on a career, one of his professors, a physicist named Philip von Jolly, actively tried to discourage him from going into physics at all. Von Jolly told him, quite sincerely, that the field was essentially finished, that all the major discoveries had already been made, and a bright young mind like his would be better off doing something else with his life, because there was nothing important left to find. Planck reportedly responded that he didn't necessarily want to discover new things. He simply wanted to understand the existing foundations of physics more deeply, more precisely. He wanted to polish what was already there, not tear it down. It's one of the great ironies in the history of science that this specific man, a person who explicitly did not want to be a revolutionary, ended up causing the single biggest revolution physics had seen since Newton. By the time Planck was working as a professor in Berlin in the late 1890s, he had turned his careful, methodical attention toward that stubborn little problem we mentioned a moment ago. The mismatch between theory and experiment when it came to how hot objects glow. Physicists at the time had extremely precise experimental data. They knew exactly how much energy a heated object radiated at every frequency of light, whether that was deep red, orange, yellow, or all the way up into the invisible ultraviolet. The measurements were beautiful, clean curves, rising smoothly to a peak and then gently falling back down. The problem was that nobody could make the math match those curves. Every attempt using classical physics, the well-tested equations of Newton and Maxwell, either worked for low frequencies and completely broke down at high ones, or vice versa, and the version that broke down at high frequencies did so in the most absurd way imaginable, predicting the object should radiate infinite energy as frequency increased. This wasn't a small numerical error you could round away. It was a total, catastrophic failure of the theory, later nicknamed, quite dramatically, the ultraviolet catastrophe. And it sat there, unresolved, right in the middle of physics's proudest era of confidence. Planck approached this problem the way he approached everything, carefully, mathematically, without any grand ambition to rewrite the laws of nature. He simply wanted to find a formula, any formula, that would match the experimental curves correctly across the entire range of frequencies. And in October of 1900, after years of careful work, he found one, a single equation that fit the data almost perfectly, matching the smooth, real-world curves with striking accuracy. But here's where the story turns strange, because Planck's formula only worked if he made one deeply weird assumption on the way there. He had to assume that the tiny vibrating structures inside hot objects, the things responsible for emitting light, couldn't release energy smoothly and continuously the way everyone had always assumed. Instead, they could only release energy in small, fixed chunks, specific indivisible packets, with nothing allowed in between. He called these packets quanta, borrowing the Latin word simply meaning how much. It wasn't meant to be a bold philosophical claim about reality. Planck treated it almost apologetically, describing this assumption later as an act of sheer desperation, something he only introduced because absolutely nothing else worked, and he fully expected some clever colleague would eventually find a proper, respectable, classical explanation that made the strange quantum assumption unnecessary. Nobody ever did. Planck spent years afterward quietly hoping his own idea would be disproven, replaced by something less unsettling. It never was. The tiny, strange assumption he'd made almost reluctantly, purely to rescue an equation from mathematical embarrassment, turned out to describe something genuinely, fundamentally true about how the universe operates at its smallest scales, and the constant he introduced to measure the size of these energy packets, a staggeringly tiny number now called Planck's constant, would go on to appear again and again throughout the rest of this story, showing up in places Planck himself never could have imagined, quietly stitching together decades of discoveries that hadn't happened yet. At the time, in December of 1900, when Planck first presented these ideas to the German Physical Society, almost nobody in that room understood what had just happened. Planck certainly didn't. He believed he had patched one narrow, technical problem in an otherwise perfectly sound classical theory. What he had actually done, without meaning to, was open a crack in the foundation of physics that would only widen from there, one that a young patent clerk working quietly in Switzerland was about to step into and blow wide open just 5 years later. That patent clerk was Albert Einstein, and in 1905, he was nothing like the wild-haired icon plastered across dorm room posters today. He was 26 years old, working as a third-class technical expert at the Swiss Federal Patent Office in Bern, reviewing other people's inventions during the day and doing physics on the side, mostly for his own satisfaction because no university had yet offered him an academic position. He didn't have a laboratory. He didn't have prestigious colleagues down the hall. He had a desk job, a young family, and a stubborn habit of thinking about the deepest questions in physics during his lunch breaks. That single year, 1905, later became known as his miracle year because in the span of about 12 months, Einstein published 4 separate papers, each one significant enough on its own to build an entire career around. One reshaped our understanding of space and time. Another proved, essentially, that atoms were real by explaining the strange jittering motion of pollen grains in water. But the paper that concerns us tonight, the one that actually won him the Nobel Prize years later, wasn't about relativity at all. It was about something almost embarrassingly simple. What happens when you shine light on a piece of metal? Scientists had known for nearly 20 years that shining light on certain metals could knock electrons loose from their surface, a phenomenon called the photoelectric effect, and under the classical theory of light, the one Maxwell had so beautifully proven, where light behaves as a smooth, continuous wave. This should have worked in a very specific, predictable way. Brighter light means a bigger wave. A bigger wave should deliver more energy, so brighter light should knock electrons off with more force, more speed, more punch. Except that's not remotely what the experiments showed. Instead, physicists found that the energy of the ejected electrons depended entirely on the color of the light, not its brightness. Shine a very dim beam of violet light on a metal surface, and you'd get electrons flying off with real energy. Shine an extremely bright beam of red light on the same metal, and sometimes, no matter how intense you made it, absolutely nothing would happen. No electrons at all. It was as if the color of the light mattered more than how much of it there was, which made no sense whatsoever under the accepted wave theory of light. Einstein's explanation was almost shockingly direct and far bolder than Planck's own reluctant idea. Planck had suggested that hot objects release energy in small packets, but he still believed light itself traveled through space as a smooth, continuous wave. Einstein pushed the idea one enormous step further. He proposed that light itself, while traveling, exists as individual, discrete packets of energy, not just released in chunks, but actually made of chunks. Decades later, these packets would be given a name, photons. But in 1905, Einstein simply called them light quanta, and the idea struck most physicists, including Planck himself, as going a step too far. Here's why Einstein's picture explained the photoelectric effect so cleanly. If light really does travel as individual packets, then hitting a metal surface with light becomes a one-on-one interaction. One photon strikes one electron. If that single photon carries enough energy to knock the electron free, it happens instantly, regardless of how many other photons happen to be around at the same time. And the energy of a single photon depends specifically on the light's frequency, its color, not on the total brightness of the beam. A violet photon simply carries more punch per particle than a red one because violet light has a higher frequency, throwing more red photons at the metal. Brightening the beam just means more weak, underpowered attempts, none of which individually carry enough energy to do the job. A million gentle taps will never accomplish what a single firm knock can. This was a genuinely radical claim, and even Max Planck, the very man whose own quantum idea had made Einstein's leap possible in the first place, thought Einstein had gone too far. Years later, when Planck wrote an official letter recommending Einstein for a prestigious academic position, he praised nearly everything about the young physicist's work, but specifically singled out the light quantum hypothesis as an example of Einstein occasionally missing the target with his speculation. In other words, Planck was essentially saying, "Brilliant scientist, wrong about this one." He wasn't wrong. Einstein's light quanta turned out to be exactly correct, confirmed by experiment after experiment in the years that followed. But here's where things get genuinely strange, the first real, deep strangeness of this entire story, because light hadn't stopped being a wave. Thomas Young's famous double-slit experiment, performed all the way back in 1801, had already proven beyond doubt that light produces interference patterns, the unmistakable signature of wave behavior, ripples overlapping and reinforcing or canceling each other out exactly the way ripples do on the surface of a pond. That evidence hadn't gone anywhere. It was still true. So now physics found itself holding two apparently incompatible facts at the exact same time. Light behaves like a wave, proven overwhelmingly, repeatedly, for over a century, and light behaves like a stream of individual particles, proven just as convincingly by Einstein's explanation of the photoelectric effect. Not one or the other, both, simultaneously. And nobody, not Einstein, not Planck, not anyone else alive in 1905, had the faintest idea how something could possibly be both of those things at once. Both, simultaneously. Sit with that for a second, because it's the first genuine paradox in this story, and it will not be the last. Light is a wave. Light is a particle. Neither description alone is enough, and yet somehow, they're both completely true at the same time. Physicists eventually gave this contradiction a proper name, wave-particle duality. But naming a paradox doesn't make it comfortable. It just gives you a word to use while you're still confused. And while Einstein was quietly wrestling with the strange dual nature of light, on the other side of the English Channel, a completely different crisis was brewing, one that had nothing to do with light at all. This one was about matter itself, about the very thing atoms are supposedly made of. By the early 1900s, physicists already knew atoms existed. They knew atoms contained tiny, negatively charged particles called electrons, discovered by J.J. Thomson back in 1897. But nobody actually knew how an atom was put together. What did it look like on the inside? Thomson himself proposed a model that became known, somewhat unfortunately, as the plum pudding model, imagining electrons scattered throughout a soft, diffuse cloud of positive charge, like raisins suspended in a pudding. It was a perfectly reasonable guess, given what little evidence anyone had at the time. Then, in 1909, in a laboratory in Manchester, England, a physicist from New Zealand named Ernest Rutherford ran an experiment that completely destroyed that comfortable picture. Rutherford's team fired a beam of tiny, fast-moving particles, essentially helium nuclei stripped of their electrons, at an extraordinarily thin sheet of gold foil. So thin it was only a few hundred atoms thick. If Thomson's plum pudding model was correct, if the positive charge inside an atom really was spread out evenly like a soft cloud, these particles should have sailed straight through with barely a wobble, the way a bullet passes cleanly through fog. And most of them did exactly that. But not all of them. A small number of particles deflected sharply at large, unexpected angles, and an even smaller fraction, a tiny, almost negligible sliver of the total, bounced almost straight back the way they came, as if they'd slammed into something incredibly small, incredibly dense, and incredibly hard. Rutherford later described his own reaction in a way that's become one of the most quoted lines in the history of physics. He said, "It was as if you fired a massive artillery shell at a piece of tissue paper, and it came bouncing straight back and hit you." After months of careful analysis, Rutherford reached an unavoidable conclusion. Almost all of an atom's mass, and every bit of its positive charge, had to be crammed into an unimaginably tiny region right at the center. He called this region the nucleus, and the scale involved was almost impossible to picture honestly. If you blew an atom up to the size of an entire football stadium, the nucleus at its center would be smaller than a marble sitting on the 50-yard line. Everything else, that entire vast stadium of space, was essentially empty, occupied only by the ghostly presence of orbiting electrons. Take a moment to actually let that sit with you, because it applies to you personally right now, lying in bed. Your body, the mattress beneath you, the walls around you, all of it at the atomic level, is almost entirely empty space. The reason your hand doesn't pass straight through the blanket has nothing to do with atoms being packed together like solid little marbles. It's the electromagnetic force between electrons creating an effective barrier, even though the underlying structure is by volume almost entirely nothing at all. This was already a strange and beautiful discovery on its own. But it came with an enormous, terrifying problem baked right into it, one that Rutherford's model had absolutely no way to solve. According to everything classical physics understood about electricity and magnetism, Rutherford's atom simply could not exist. Not shouldn't exist for philosophical reasons, could not physically exist according to well-established, thoroughly tested equations. Here's why. A negatively charged electron orbiting a positively charged nucleus is constantly changing direction. And according to James Clerk Maxwell's own equations, any charged particle that accelerates, and circular motion always counts as acceleration, must continuously radiate energy away as electromagnetic waves. An orbiting electron should be leaking energy the entire time it circles the nucleus, losing momentum, spiraling closer and closer inward with every loop, exactly the way a satellite losing altitude eventually crashes down to Earth. And the math on this wasn't vague or uncertain. Physicists calculated that this collapse should happen almost instantly. Within roughly 100 billionth of a second, every single atom in the entire universe should have violently self-destructed the moment it formed, collapsing in on itself in a tiny burst of radiation almost as soon as it came into being. Obviously, that catastrophe never happened. You exist. The stars are burning steadily rather than flashing out of existence in an instant. Chemistry works exactly the way it's supposed to, atom by stable atom. Something somewhere was preventing this collapse from happening. But classical physics had absolutely no explanation for what that something might be. By around 1911 and 1912, physicists were staring directly at an atomic model that fit their experimental evidence beautifully, and yet appeared to be flatly impossible. According to the very same laws of physics, that had built that evidence in the first place. Rutherford had handed the world the correct basic architecture of the atom, a dense nucleus surrounded by orbiting electrons, but nobody could explain why that architecture didn't instantly destroy itself. And into that exact contradiction stepped a quiet, unusually thoughtful young physicist from Denmark, about to propose something so strange, so deliberately unclassical, that it would either save the atom or make the entire situation even more confusing. That quiet young physicist was Niels Bohr, and understanding him requires understanding something almost paradoxical about the way his mind worked. He was famously slow. Colleagues sometimes left his lectures more confused about what he'd actually claimed than when they walked in, because Bohr expressed his ideas in careful, hedged, heavily qualified language, turning a problem over and over from every possible angle before committing to anything. But when he finally did commit, he was usually right, and the depth underneath his tangled sentences tended to be extraordinary. Bohr was born in Copenhagen in 1885, raised in a household that treated ideas as something worth arguing passionately about at the dinner table. After finishing his doctorate, he traveled to England, first working briefly with J. Thomson at Cambridge, a relationship that apparently didn't click especially well, before moving on to Manchester to work directly with Ernest Rutherford. And it was there, staring straight at Rutherford's beautiful, doomed atomic model, that Bohr made a genuinely audacious decision. He didn't try to rescue classical physics. He didn't go hunting through Maxwell's equations looking for some clever loophole that might stabilize the orbiting electron. Instead, in 1913, Bohr essentially declared that classical physics simply didn't apply here, full stop, and then he invented an entirely new rule to replace it. His idea was this: electrons aren't free to orbit a nucleus at any distance they please. Instead, they're restricted to a specific, limited set of allowed orbits, and while sitting in one of these allowed orbits, an electron simply does not radiate energy. Not because some hidden classical mechanism is quietly preventing it. It just doesn't, because that's apparently how the universe is built at this scale. It was a rule imposed from outside classical physics entirely, an axiom rather than a derived consequence, and Bohr openly admitted he didn't know why it should be true. He just knew that if he assumed it, the numbers worked out, and which orbits counted as allowed. This is where Planck's tiny constant reappeared. 9 years after, it was first introduced to solve a completely unrelated problem about glowing metal. Bohr proposed that an electron's angular momentum, essentially a measure of how much rotational motion it carries, had to be a whole number multiple of Planck's constant divided by a specific factor, not 1.5 times, not 2.3 times, only whole numbers, 1, 2, 3, and so on, with absolutely nothing allowed in between. The electron could occupy the first allowed orbit, or the second, or the third, but never anywhere in the gaps. This meant an electron couldn't smoothly spiral inward the way classical physics demanded. Instead, it could only make sudden, discrete jumps between these fixed, allowed orbits, and when it made one of those jumps, dropping from a higher orbit down to a lower one, it released the energy difference between the two levels as a single photon, a tiny burst of light carrying precisely that amount of energy and no more. Jump up to a higher orbit, and the electron had to absorb a photon carrying exactly that same specific amount of energy first. Here's why this mattered so enormously. For decades, scientists had known that heating up a particular gas, like hydrogen, and passing the light it emitted through a prism didn't produce a smooth rainbow. Instead, it produced a distinct pattern of sharp, bright lines at very specific wavelengths, with darkness everywhere else, almost like a barcode unique to each element. Back in 1885, a Swiss schoolteacher named Johann Balmer had discovered a simple mathematical formula that predicted the exact positions of these lines for hydrogen with remarkable precision, but nobody had any idea why that formula worked. It was treated as a strange numerical coincidence with no underlying explanation. Bohr's model explained it perfectly. When he calculated the specific allowed energy levels for an electron orbiting a hydrogen nucleus, and then worked out the exact energy of photons that would be released. As electrons jumped between those levels, the numbers matched Balmer's decades-old formula almost exactly, not approximately, precisely. That kind of agreement is difficult to dismiss as coincidence, and physicists across Europe took immediate notice. Even Einstein, upon hearing about the results, reportedly called it one of the greatest discoveries in the history of science. But Bohr's model, for all its predictive power, had an obvious, glaring gap sitting right at its center. It worked because Bohr had simply declared, by decree, that certain orbits don't radiate energy. He hadn't explained why nature would follow such a rule. It felt exactly like what it was, a patch, a postulate handed down from outside the theory rather than something derived naturally from deeper principles. Rutherford himself, impressed but visibly uneasy, wrote to Bohr directly asking a pointed question that cut right to the heart of the problem. How, exactly, does an electron decide which orbit to jump to, and when does it decide to make that jump? Bohr didn't really have an answer. There was also a more practical embarrassment lurking underneath the theoretical one. Bohr's model worked beautifully for hydrogen, the simplest possible atom, with just a single electron orbiting a single proton. But the moment physicists tried applying the same rules to helium, with 2 electrons instead of 1, or to any heavier element on the periodic table, the model fell apart completely. It couldn't accurately predict the spectral lines of anything more complicated than the simplest atom in existence. It was, in a sense, a key that opened exactly one door and fit absolutely nothing else in the building. Something deeper was clearly still missing, some more general framework capable of explaining not just hydrogen, but the entire periodic table, and eventually all of chemistry itself. That deeper framework wouldn't arrive for another decade, and when it finally did, it would come from an entirely unexpected direction, starting with a question posed not by a career physicist at all, but by a French aristocrat with a title, a family history steeped in politics and warfare, and a genuinely strange idea about waves. That French aristocrat was Louis de Broglie, and his path into physics wasn't a straight line at all. The de Broglie family had been prominent in French politics and military affairs for centuries, and Louis himself actually held the formal title of prince. He started out studying history at the Sorbonne in Paris, with every intention of building a career in the humanities, nothing to do with physics whatsoever. But his older brother Maurice was a working physicist studying X-rays, and something about the family's dinner table conversations, radiation, atoms, the strange new physics emerging out of Germany, gradually pulled Louis away from history and into science instead. By 1923, he was working on his doctoral thesis, and he found himself circling one particular question over and over. refusing to let it go. Einstein had already shown, with the photoelectric effect, that light, something everyone had always treated purely as a wave, could also behave like a stream of individual particles. De Broglie's question was almost embarrassingly simple. Once you hear it out loud, if that's true, shouldn't the reverse also hold? Shouldn't matter, the stuff we've always treated purely as particles, also be capable of behaving like a wave? Take a moment to actually appreciate how bold that idea is. An electron is a tiny, physical speck of stuff. It has mass. It has charge. You can bend its path with a magnet. It leaves visible tracks when it moves through certain detection chambers, exactly the way you'd expect a solid little particle to behave. De Broglie was proposing that this same, apparently solid object also has a wavelength, that it ripples, that it can interfere with itself, the exact same way light passing through two narrow slits produces an interference pattern. He didn't leave this as a vague philosophical suggestion either. He wrote down an actual formula. The wavelength of any particle, he proposed, equals Planck's constant divided by that particle's momentum. Simple, elegant, and there, sitting right in the middle of the equation, once again, was that same tiny number Planck had introduced more than 2 decades earlier, purely as a mathematical trick to fix a problem about glowing metal. It kept reappearing throughout this story, like a single thread running quietly underneath everything. Here's why this idea, on its face, seemed almost too strange to take seriously. The wavelength you calculate from de Broglie's formula depends directly on an object's momentum, which is simply mass multiplied by velocity. For anything you could actually hold in your hand, a baseball, a grain of sand, even something as small as a bacterium, the mass involved is so enormous compared to Planck's constant that the resulting wavelength comes out absurdly, unimaginably tiny, far smaller than an atomic nucleus, utterly undetectable in any practical sense. That's precisely why the everyday world around you doesn't feel wavy in any obvious way. But for something as genuinely light as an electron, the calculated wavelength turns out to be roughly the same size as an atom itself. And that changes absolutely everything. Remember Bohr's strange, unexplained rule that electrons could only occupy certain fixed orbits, with nothing in between allowed. De Broglie's idea finally gave that rule an actual physical explanation, rather than just an arbitrary decree. If an electron behaves like a wave while circling a nucleus, that wave has to connect smoothly back with itself after traveling all the way around the loop. It has to form what's called a standing wave, the same basic principle behind a plucked guitar string, which can only vibrate in certain specific patterns, never in some arbitrary, unstable in-between shape because its two ends are fixed in place. Apply that same logic to an electron wave wrapped around a nucleus, and the circumference of any stable orbit has to contain a whole number of wavelengths, 1, 2, 3, and so on, never 1.5, never 2 3/4. If the wave doesn't fit evenly, it interferes with itself destructively and simply cancels out, meaning that orbit can't physically exist. Work through the math carefully, and the orbits where the electron wave does fit perfectly turn out to be exactly the same. Orbits Bohr had proposed years earlier, purely as an unexplained postulate. Bohr's arbitrary-seeming rule wasn't arbitrary at all. It was a direct, natural consequence of electrons behaving like waves in exactly the same way a flute can only ever produce certain specific notes, never the infinite continuum of pitches in between. de Broglie presented this idea in his doctoral thesis in 1924, and his examining committee genuinely wasn't sure what to make of it. It was elegant, it was mathematically clean, but it was also undeniably a claim that everything made of matter secretly behaves like a wave, which isn't the sort of thing an academic committee simply nods along with. One of the examiners sent the thesis directly to Einstein for a second opinion, and Einstein reportedly responded that de Broglie had lifted a corner of a very heavy veil. That endorsement was enough. The thesis was accepted, and de Broglie eventually won the Nobel Prize for the idea in 1929. More importantly, his prediction wasn't left as pure theory for long. In 1927, at Bell Labs in New York, two researchers named Clinton Davison and Lester Germer fired a beam of electrons directly at a crystal of nickel and observed something that should have been impossible if electrons were simple, ordinary particles, a diffraction pattern, the unmistakable signature of wave behavior produced by electrons bouncing off the regularly spaced atoms inside the crystal, exactly the way X-rays scatter off crystal structures. Around the same time, working independently in England, a physicist named George Paget Thomson demonstrated the same electron diffraction effect using thin metal films. And in one of those details of history that feels almost too perfectly ironic to be real, George Thomson happened to be the son of J.J. Thomson, the very same physicist who had originally discovered the electron as a particle 3 decades earlier. The father proved the electron was a particle. The son proved it was also a wave. Both men eventually won Nobel Prizes for their work. Both of them were completely right, which, by this point in the story, should stop surprising you. By the mid-1920s, the pieces were piling up fast, and none of them fit together comfortably yet. Energy came in discrete chunks. Light behaved as both wave and particle. Matter, apparently, did the exact same thing. And Bohr's model, elegant as it was for the simplest possible atom, completely fell apart for anything more complicated. What physics desperately needed now wasn't another patch, another clever exception bolted onto an already strained framework. It needed something entirely new, a complete mathematical system, built from the ground up to handle this strangeness properly. And in an almost unbelievable coincidence of timing, two completely different young physicists, working independently, using completely different mathematical approaches, were about to arrive at exactly that framework within months of each other. The first of those two physicists was Werner Heisenberg, and the story of how he stumbled onto his breakthrough involves, of all things, a bad allergy attack. In the summer of 1925, Heisenberg was 23 years old, working as an assistant to the physicist Max Born in the German university town of Göttingen. He was brilliant, restless, and, that particular summer, suffering terribly from hay fever, bad enough that the pollen in the air made it almost impossible for him to think clearly. So he requested leave and traveled to Helgoland, a small, rocky, wind-battered island out in the North Sea, with almost no vegetation at all, and therefore almost no pollen to torment him. Alone out there, finally able to breathe and think clearly, Heisenberg worked through a radically different approach to the atomic puzzle. Instead of trying to picture what an electron was actually doing as it moved, where exactly it was, what path it traced through space, he decided to throw all of that out entirely. You can't see an electron orbiting a nucleus. You can't watch it trace a path with your own eyes. What you actually can measure directly in a laboratory are the frequencies and brightness of the specific light that atoms emit and absorb, those same sharp spectral lines that had puzzled physicists for decades. So Heisenberg decided to build an entirely new kind of physics using only quantities that could actually be observed and measured, nothing more. He constructed elaborate mathematical tables, essentially grids of numbers, representing the relationships between different possible energy states inside an atom and the probabilities of an atom jumping between them. He wasn't asking where the electron was. He was only asking what could be measured about it from the outside. The mathematics that came out of this approach turned out to behave in a genuinely strange way. When Heisenberg multiplied two of his number tables together, the order in which he multiplied them actually changed the final result. In ordinary arithmetic, of course, 3 times 5 gives you exactly the same answer as 5 times 3. But Heisenberg's quantities didn't cooperate that way at all. He found this so unsettling that he stayed up through the entire night, double and triple checking his calculations, convinced he'd made some careless mistake. By roughly 3 in the morning, once he'd confirmed the strange result held up, he was too excited to sleep at all, and instead walked out to the edge of the island to watch the sun come up over the water, knowing he'd stumbled onto something enormous, even if he didn't yet fully understand what it was. When he brought the work back to Göttingen, Max Born immediately recognized the underlying mathematical structure. Heisenberg had essentially reinvented something mathematicians already called matrix algebra, and the fact that multiplying his tables in different orders gave different results was simply a known, fundamental property of matrices. Born, working together with a young mathematician named Pascual Jordan, helped formalize Heisenberg's raw insight into a complete self-consistent theory that became known as matrix mechanics. It was the very first fully working mathematical framework for quantum physics, and it genuinely worked, correctly predicting the spectral lines of hydrogen and successfully extending to more complicated atoms as well. There was just one significant problem. It was almost impossibly abstract. There was no picture attached to any of it, nothing you could visualize happening physically, just enormous grids of numbers governed by strange algebraic rules. Most working physicists at the time found it brutally difficult to use, mathematically correct, but emotionally and intuitively unsatisfying, like being handed the right answer with absolutely no sense of why it was right. And then, just a few months later, in early 1926, an entirely different physicist arrived at essentially the same destination from a completely different direction. His name was Erwin Schrödinger, an Austrian physicist already in his late 30s, notably older than most of the other young revolutionaries working on this problem, and he had been directly inspired by de Broglie's idea of matter waves. Schrödinger's reasoning was straightforward. If electrons genuinely behave as waves, he thought, then there should logically exist an actual wave equation governing their behavior, the same way James Clerk Maxwell's equations govern electromagnetic waves, or the way a much simpler equation from classical physics governs vibrations traveling along a plucked string. So, Schrödinger set out to find that equation, and the circumstances surrounding his discovery have become one of those legendary, slightly scandalous stories that historians of science still enjoy retelling. In December of 1925, Schrödinger traveled to a villa in the Swiss Alps for a holiday. accompanied, according to historical accounts, by a woman who was not his wife and whose identity has never been definitively confirmed. During those few intensely productive weeks in the mountains, he worked out the equation that now permanently bears his name, the Schrödinger equation, describing how a mathematical object called the wave function evolves and changes over time. Unlike Heisenberg's abstract grids of numbers, Schrödinger's equation looked comfortably familiar to physicists trained in classical mathematics. It was what's called a differential equation, exactly the kind of math scientists had already used for centuries to describe fluids, heat flow, and vibrations. You could actually picture something happening, imagining the wave function as an actual physical wave, sloshing and spreading through space, the way ripples spread across a pond. Schrödinger himself initially believed the wave function represented something genuinely physically real, that an electron literally was a wave continuously throughout space, and his equation simply described that waves changing shape over time. Physicists loved this new approach immediately. It felt intuitive, it felt powerful, and remarkably, it produced exactly the same predictions as Heisenberg's far more abstract matrix mechanics for every single problem anyone tested it against, which created an obvious, pressing question. Were these genuinely two completely different theories that just happened to agree by some strange coincidence? Or were they secretly the exact same underlying theory, simply written in two different mathematical languages? Schrödinger himself answered that question later in 1926, proving mathematically that his wave mechanics and Heisenberg's matrix mechanics were fully equivalent, just two different ways of describing the identical underlying physics, roughly analogous to how you can describe the exact same circle using either standard coordinates or a completely different coordinate system, arriving at the same shape either way, just written down differently. But solving that particular mathematical puzzle immediately opened up a far bigger, far more uncomfortable question, one that would end up consuming physics for the rest of the century, and quite honestly still hasn't been fully settled today. Because having the right equations, ones that produced perfectly accurate predictions every single time, was not remotely the same thing as understanding what those equations were actually telling us about reality itself. What exactly was this strange wave function supposed to represent? And the answer that emerged next would turn out to be far stranger and far more unsettling than either Heisenberg or Schrödinger had initially bargained for. The man who forced that uncomfortable question into the open was Max Born, the very same physicist who had helped Heisenberg formalize his matrix mechanics back in Göttingen. And what Born noticed was a problem sitting quietly inside Schrödinger's own beautiful equation, one that Schrödinger himself hadn't fully reckoned with yet. When you actually solve the Schrödinger equation for something like an electron inside an atom, the resulting wave function doesn't describe a tidy point sitting at one specific location. It spreads out smoothly and continuously across an entire region of space. If Schrödinger was right that this wave function represented something physically real, an electron literally smeared out like a cloud, then you'd expect experiments to occasionally catch a fraction of an electron here and another fraction there, distributed across space the way the equation describes. But that is never what happens. Every single time physicists actually measured an electron's position, they found it sitting at one single, definite location, never smeared out, never split into pieces. You never detect half an electron in one place and half in another. So the wave function, whatever it actually represented, could not literally be the electron itself. Spread thin across space, like some kind of diffuse cloud, Bohr proposed something different and considerably more unsettling. He suggested that the wave function doesn't describe where a particle actually is. It describes the probability of finding that particle at any given location, if you happen to measure it. Specifically, mathematically, the square of the wave function at any particular point in space tells you the odds of detecting the particle there. Before you take a measurement, the electron doesn't have some hidden, definite position that you simply don't happen to know yet. According to Bohr's interpretation, there genuinely is no definite position at all, only a spread of possibilities, until the moment a measurement forces one specific outcome to occur. The instant you do measure it, that entire spread of possibilities collapses down to a single, definite result. The wave function, describing a whole cloud of potential outcomes an instant earlier, suddenly snaps into a single sharp point the moment observation happens. Sit with that for a second, because this genuinely was a profound and unsettling shift, one that went far beyond anything physics had ever claimed before. For the first time in the entire history of science, a fundamental physical theory was asserting that nature, at its deepest level, is not simply unpredictable because our instruments are imperfect or our knowledge is incomplete. It is inherently, fundamentally random, in a way that no amount of additional information could ever fix. Not, we don't currently know where the electron is. Genuinely, there is no fact about where the electron is until something forces the question. This probabilistic interpretation, alongside a related set of ideas developed by Niels Bohr, became known as the Copenhagen interpretation of quantum mechanics, and it quickly became the dominant working view among most physicists actively using the theory day to day. It wasn't universally beloved, far from it, and the person who objected most persistently, most publicly, and most eloquently happened to be someone you've already met earlier in this exact story, the very same physicist who had helped kick off the entire quantum revolution in the first place with his explanation of the photoelectric effect. Albert Einstein had deep, principled objections to the idea that the universe operates on pure, irreducible chance. He famously summarized his discomfort by saying that God does not play dice with the universe, and the resulting disagreement between Einstein and Bohr over what quantum mechanics actually meant would become one of the most celebrated intellectual confrontations in the entire history of science. It wasn't petty. It wasn't simple stubbornness, though both men certainly had plenty of that in their personalities. It was a genuine, deeply felt disagreement about the fundamental nature of reality itself, about whether the universe, at its core, actually is knowable in the specific, definite way physicists had always assumed it must be. Here's a distinction worth holding on to clearly, because it matters enormously for everything still ahead in this story. Nobody, including Einstein, disputed that the math of quantum mechanics worked. The equations produced numbers that matched experimental results with extraordinary precision over and over again across every test anyone devised. What Einstein disputed was what that math actually meant about the underlying nature of reality. Having a working formula isn't automatically the same thing as understanding what's genuinely happening underneath it. You can follow a recipe that reliably produces a perfect cake every single time and still have absolutely no idea why that particular combination of ingredients produces that particular result. Einstein wanted the why. He wanted to know what was actually happening out there in the physical world, whether or not anyone happened to be looking at it. And the Copenhagen interpretation, as championed by Bohr and Heisenberg, essentially responded that this specific question doesn't have a meaningful answer at all. According to Copenhagen, the wave function represents the single most complete description of a quantum system that is possible, full stop. There is no hidden, deeper layer sitting underneath it, waiting to be discovered with better instruments or cleverer mathematics. If you ask where an electron actually is before you measure it, Copenhagen's answer isn't, "We don't know yet." It's that the electron simply doesn't possess a definite position at all until the measurement happens. The act of measuring doesn't reveal some pre-existing fact that was quietly sitting there all along. In a very real sense, it creates that fact right at the moment of observation. If your first reaction to that idea is something like genuine disbelief, you are in remarkably good company. Einstein felt exactly the same way, and he wasn't confused about the underlying mathematics. He could follow the equations as skillfully as almost anyone alive. His objection ran much deeper than that. It cut against something fundamental in his physical intuition about how reality itself ought to behave. Whether or not a conscious observer happened to be paying attention to it at any given moment, this deep, unresolved disagreement between two of the greatest scientific minds of the 20th century wasn't going to stay quiet in academic journals for long. It was about to spill out into a series of legendary face-to-face confrontations, arguments conducted over breakfast tables at exclusive scientific gatherings in Belgium, where Einstein would spend years constructing increasingly clever traps designed to expose a flaw in quantum mechanics. And Bohr would spend those same years scrambling, sometimes desperately, to find his way back out of each one. Those legendary confrontations played out at a series of scientific gatherings called the Solvay Conferences, held in Brussels and funded by the wealthy Belgian industrialist Ernest Solvay. These were invitation-only meetings that brought together the most brilliant physicists alive at the time, and the 1927 conference in particular has become genuinely famous, immortalized in a single black and white photograph you have almost certainly seen somewhere, even if you never knew what it was. Rows of serious-looking men and one woman in formal dress, and among them, standing or sitting together in the same room at the same moment, are Einstein, Bohr, Heisenberg, Schrödinger, Max Born, and Marie Curie, alongside a dozen or so other towering figures in physics. Of the 29 people photographed that day, 17 either had already won or would eventually go on to win a Nobel Prize. It's arguably the single most extraordinary gathering of scientific minds ever assembled in one room, and it happened while Einstein and Bohr were locked in an argument that neither of them was willing to lose. Einstein's strategy at these conferences was clever, and it was never really about the math itself. He knew perfectly well that the equations of quantum mechanics produced accurate predictions. Instead, he constructed elaborate thought experiments, carefully designed hypothetical scenarios meant to demonstrate that the theory, whatever its practical success, couldn't possibly be the complete picture of reality. There had to be some deeper, more sensible layer. Underneath it, he believed, one that would eventually restore the kind of definite, deterministic certainty that classical physics had always provided. Before quantum mechanics arrived and complicated everything. At breakfast each morning, Einstein would present Bohr with some ingenious new scenario, often involving elaborate imaginary devices with slits, screens, shutters, and precisely timed clocks, all constructed to show that you could, in principle, know both the exact position and the exact momentum of a particle simultaneously, something Heisenberg's uncertainty principle explicitly forbade. Bohr would spend the entire day pacing, muttering to himself, working through the logic piece by piece, visibly troubled, and by dinner, almost without fail, he would have found the hidden flaw in Einstein's setup. Einstein would build an elegant trap. Bohr would find the escape hatch hiding inside it. One particularly famous example unfolded 3 years later at the 1930 Solvay Conference. Einstein proposed a thought experiment involving a sealed box filled with radiation, equipped with a precisely timed shutter that would open briefly enough to release exactly one single photon. By weighing the box carefully before and after the shutter opened, and using Einstein's own famous equation relating mass and energy, you could calculate the exact energy of that escaped photon from the tiny corresponding change in the box's mass. And because you knew exactly when the shutter opened and exactly how much energy left the box, you would apparently know both the precise timing and the precise energy of that photon simultaneously, violating a different version of Heisenberg's uncertainty principle that governs energy and time together. This particular challenge genuinely rattled Bohr. By most historical accounts, he spent that entire evening visibly distressed, unable to immediately spot the flaw in Einstein's reasoning. But by the following morning, he had found it, and the way he found it carries a wonderfully ironic twist. Bohr used Einstein's own general theory of relativity to defeat Einstein's own thought experiment. He pointed out that the act of weighing the box necessarily causes it to shift slightly within a gravitational field, and according to general relativity, a clock that moves within a gravitational field experiences a subtle form of time dilation, ticking at a very slightly different rate. That tiny shift in the box's position introduces just enough unavoidable uncertainty in the exact timing of the shutter's opening to preserve Heisenberg's principle perfectly intact. Einstein had been defeated quite elegantly by his own theory. Take a moment to actually appreciate what that means. Einstein, arguably the single greatest physicist who had ever lived, spent years constructing his most careful, most ingenious attempts to expose a genuine logical contradiction hiding somewhere inside quantum mechanics, and he simply could not find one. That doesn't prove quantum mechanics is correct in some final, ultimate philosophical sense, but it does demonstrate something remarkable about how robust and internally consistent the framework actually is, resistant even to attacks from the most brilliant mind attempting to dismantle it. Einstein characteristically didn't give up after this defeat. He simply changed his approach entirely. Rather than continuing to hunt for a logical contradiction buried inside the theory, he shifted his focus toward arguing that quantum mechanics, whatever its internal consistency, was fundamentally incomplete, that it was missing some deeper layer of description that a proper, more thorough theory would eventually need to include. And this new line of thinking led directly to one of the single most famous and consequential papers in the entire history of physics. In 1935, Einstein, working together with two younger colleagues named Boris Podolsky and Nathan Rosen, published a paper universally referred to by their initials EPR. Its title asked a deceptively simple question: can the quantum mechanical description of physical reality be considered complete? Their carefully constructed answer, argued across the entire paper, was no. Here's the basic setup, simplified somewhat from their original, denser version. Imagine a source that produces two particles simultaneously, launching them off in opposite directions, created in such a specific way that their properties become permanently correlated with each other. Quantum mechanics calls this phenomenon entanglement, a term Erwin Schrödinger actually coined that same year, describing it as the single characteristic trait that most distinguishes quantum mechanics from everything that came before it. Suppose these two particles are correlated in such a way that if you measure one and discover it's spinning in one particular direction, the other particle, no matter how far away it currently is, must instantly be spinning in the exact opposite direction. Quantum mechanics predicts this correlation precisely, and it has since been confirmed experimentally an enormous number of times in laboratories all over the world. Here comes the crucial part of Einstein's argument, the part that would end up haunting physics for decades to come. According to the Copenhagen interpretation, neither particle actually possesses a definite spin direction at all until the exact moment someone measures it. The spin is genuinely, fundamentally undetermined, floating in a cloud of pure possibility. But the very instant you measure one particle and discover it's spinning clockwise, you instantly know, with absolute certainty, that the other particle must be spinning counterclockwise, even if that second particle currently sits somewhere on the opposite side of the entire galaxy. How does that distant second particle possibly know instantaneously what result its distant twin just produced? How does that information travel across such an enormous distance with apparently zero delay? If it happens truly instantaneously, that would seem to violate Einstein's own special theory of relativity, which explicitly forbids anything from traveling faster than the speed of light. Einstein gave this apparent contradiction a memorably dismissive nickname of his own, calling it spooky action at a distance. And he meant it as an insult. He thought the entire idea was simply absurd, a clear sign that something essential was still missing from quantum theory. And the argument he built around that objection would sit there, unresolved, refusing to quietly disappear for the next 3 decades. That objection sat there for nearly 30 years, mostly ignored by working physicists, treated more as a philosophical curiosity than a real scientific dispute. And in a sense, that made perfect practical sense. The equations of quantum mechanics worked identically, no matter which side of the argument you personally believed. You could privately think Einstein was right, that hidden variables must exist somewhere beneath the surface. Or you could side fully with Bohr and the Copenhagen interpretation, and your actual calculations, the numbers you'd use to predict experimental results, wouldn't change one single digit either way. It was treated, almost universally, as a matter of philosophical taste rather than genuine physics. Then, in 1964, an Irish physicist working at CERN, the major European particle physics laboratory near Geneva, changed that assumption completely. His name was John Stuart Bell, and he had been quietly turning the EPR argument over in his mind for years. What Bell eventually produced was remarkable precisely because of how deceptively simple it was. He asked a question nobody else had managed to formulate properly before him. Was there any actual, measurable, experimental difference between standard quantum mechanics and any possible version of Einstein's local hidden variables idea? The notion that particles secretly carry definite, predetermined properties all along, with information never actually traveling faster than light between them? The answer, remarkably, turned out to be yes. Bell derived a specific mathematical inequality, now simply known as Bell's inequality, that any theory built on local hidden variables would necessarily have to satisfy, no exceptions. Picture it like an absolute speed limit. If the universe genuinely worked the way Einstein hoped, with particles secretly carrying fixed, predetermined properties, and no faster-than-light influence connecting them, then certain statistical correlations measured between entangled particles could never rise above a specific mathematical ceiling. But standard quantum mechanics predicted that, under the right experimental conditions, this ceiling would be broken. The correlations would come out stronger than any local hidden variables theory could possibly produce, no matter how cleverly constructed. This was no longer an abstract philosophical disagreement. It had become a concrete, testable prediction. You could actually walk into a laboratory, generate pairs of entangled particles, take careful measurements, tally the resulting statistics, and directly check whether Bell's inequality held true or was genuinely violated. Starting in the 1970s, physicists began doing exactly that. The most famous and rigorous of these early experiments were carried out by a French physicist named Alain Aspect and his research team at the University of Paris-Sud. In 1981 and 1982, Aspect's experimental design was genuinely ingenious. He used pairs of entangled photons produced by exciting calcium atoms, then measured their polarization at carefully chosen angles. Crucially, he built in a feature specifically designed to close one of the biggest potential loopholes in earlier tests. He rapidly switched the measurement settings while the photons were still actively in flight, traveling between the source and the detectors, so that neither photon could possibly know in advance which specific measurement it was about to face. There simply wasn't enough time for any signal, even one traveling at the absolute speed of light, to pass between the two detectors before the measurements were locked in. The results were unambiguous. Bell's inequality was violated, clearly and repeatedly. The measured correlations matched exactly what standard quantum mechanics predicted, and they were stronger than any local hidden variables theory could ever explain, no matter how it was constructed. Einstein's hope that particles secretly carry definite properties all along, and that quantum mechanics was simply an incomplete description of some deeper, sensible, deterministic reality underneath, was experimentally ruled out, not philosophically debated into a stalemate. Actually, physically ruled out in a real laboratory using real photons. It's worth being precise here because this detail genuinely matters. What Bell's theorem and Aspect's experiments ruled out was the specific combination of locality and hidden variables together. You can still, if you're determined enough, hold on to hidden variables as an idea, but only if you're willing to give up locality entirely, accepting some kind of influence that genuinely does connect distant particles instantaneously. in direct tension with our everyday intuitions about cause and effect unfolding in an orderly sequence across space. Most physicists chose instead to accept that quantum mechanics really is describing something genuinely non-local and genuinely probabilistic at its core, exactly as Bohr had always maintained. Consider, for a moment, the sheer weight of what just happened. Albert Einstein, arguably the single most brilliant physicist who ever lived, spent literally decades of his professional life constructing his most careful, most sophisticated arguments against quantum mechanics, convinced there had to be something more sensible hiding underneath its strange predictions. And the universe itself, when physicists finally figured out how to ask it directly through Bell's clever mathematical test, sided decisively with Bohr instead. There's something genuinely poignant sitting inside that outcome. Einstein passed away in 1955, 9 full years before Bell even published his theorem, and decades before Aspect's experiments provided the final definitive confirmation. He never lived to see the very question he'd raised so persistently, so brilliantly, finally answered with total experimental clarity. But let's not rush too quickly toward declaring a simple winner and a simple loser here, because the actual story carries more nuance than that. Einstein may well have been wrong about hidden variables specifically, but the deeper questions he insisted on, raising about entanglement, turned out to matter enormously, in ways nobody at the time could have possibly predicted. Entanglement isn't merely a strange philosophical curiosity anymore. It has become an actual, usable physical resource, one that engineers and physicists now build real technology around. It sits directly underneath quantum computing, quantum cryptography, and quantum teleportation of information across distances. The very phenomenon Einstein once dismissed as merely spooky has quietly become one of the most valuable physical resources humanity has ever discovered how to harness, and understanding exactly why that's true means stepping forward now, out of the history books entirely, and into laboratories and factories that are actively running right now, in 2026, built directly on top of everything we've just walked through together. To understand how something as strange as entanglement eventually turned into working technology, we need one more piece of the puzzle first, a rule that explains something you've been lying on top of this entire time without ever thinking about it. Why matter is solid at all. Back in the 1920s, right around the same period, Heisenberg and Schrödinger were racing toward their competing versions of quantum mechanics. An Austrian physicist named Wolfgang Pauli was wrestling with a much quieter, less flashy problem. Why do electrons in an atom stack up into distinct layers, or shells, instead of all collapsing down into the single lowest, most comfortable energy level available? If electrons simply behaved like tiny balls, settling into the most stable position possible, you'd expect every single one of them to crowd into the exact same lowest orbit, the way water always seeks the lowest point in a valley. But that's not what happens at all. And if it did happen, chemistry as we know it simply wouldn't exist. In 1925, Pauli proposed a rule that would come to be called the Pauli exclusion principle, and it's almost deceptively simple to state. No two electrons within the same atom can occupy exactly the same quantum state at the same time. Electrons carry a property called spin, an intrinsic form of angular momentum that can point in one of two directions, informally described as up or down. Because of this, each specific energy level inside an atom can hold at most 2 electrons, one spinning up, one spinning down, and once that pair is full, any additional electron is completely forbidden from joining them there. It has no choice but to occupy the next available higher energy level instead. Think about what that actually forces to happen. Electrons are essentially required to stack upward, layer by layer, into higher and higher energy states, not because some external force is physically pushing them there, but because the fundamental rules of quantum mechanics simply forbid them from all crowding into the same lowest state together. It behaves almost like an elaborate, cosmic game of musical chairs, where every single chair can hold exactly 2 players and no more. And once a chair is occupied, every additional player is forced further and further up the ladder. Whether they'd prefer that or not, this one rule, quiet and unglamorous as it sounds, turns out to be the actual reason solid matter exists in a form recognizable to you at all. Without the Pauli exclusion principle, atoms wouldn't have distinct chemical properties. There would be no periodic table with its elegant repeating structure of rows and columns, no chemistry, no biology, no you. It's also, quite directly, the reason your hand doesn't simply pass straight through the mattress you're lying on right now. When you push against any solid surface, you aren't actually feeling atoms bumping into other atoms like tiny billiard balls. You're feeling the electrons in your hand being firmly, forcefully prevented from occupying the same quantum states as the electrons already sitting inside the object you're touching. Solidity itself, the entire physical sensation of one thing being unable to pass through another, is a direct, everyday consequence of this strange quantum rule. Now hold that idea, because it becomes the foundation for something enormous. Something sitting inside your phone, your laptop, and very likely the device charging somewhere near your bed right now. Consider a material like silicon, the element that makes up ordinary beach sand and, not coincidentally, the backbone of almost every computer chip ever manufactured. In pure silicon, every atom bonds neatly with 4 neighboring atoms, sharing electrons in a tidy, evenly balanced structure. At low temperatures, this arrangement leaves essentially no free electrons available to carry any electrical current at all. Pure silicon, left completely alone, is a fairly poor conductor of electricity. But now, replace just one silicon atom in that structure with a phosphorus atom instead. Phosphorus happens to have 5 outer electrons rather than silicon's 4. 4 of those electrons slot neatly into the existing bonding structure, exactly like silicon's own electrons do. But that 5th electron has nowhere comfortable to go. It's only loosely attached, and at ordinary room temperature, it breaks free easily, becoming a mobile charge carrier able to move through the material. Congratulations! You've just created what engineers call an N-type semiconductor, named for the negative charge of its extra, freely moving electrons. Now try the opposite experiment. Replace a silicon atom instead with a boron atom, which has only 3 outer electrons rather than 4. Boron can only fill 3 of the 4 available bonding slots, leaving one conspicuous gap, a missing electron, often called a hole. That hole behaves almost like a positively charged particle in its own right, capable of moving through the material. As neighboring electrons hop over to fill it, one after another, effectively shifting the hole's position each time. This produces what's called a p-type semiconductor, this time named for the effectively positive charge carried by these mobile holes. Individually, These two variants of silicon aren't especially remarkable, but place an N-type semiconductor and a P-type semiconductor directly next to each other, forming what's called a p-n junction, and something genuinely useful starts to happen. Electrons and holes can move across that boundary in one direction far more easily than the other, which means the junction allows electrical current to flow one way while blocking it almost entirely in the reverse direction. That simple, elegant property, a direct consequence of quantum mechanical rules about how electrons are permitted to arrange themselves inside matter, turns out to be the fundamental building block underneath every microchip, every smartphone, and every computer ever built. And this is exactly where our story is about to leave the tidy, orderly world of theoretical physics behind entirely and step directly into a cramped laboratory at Bell Labs in New Jersey in the final week of 1947, where two physicists took this quiet quantum mechanical property of silicon and germanium and built, almost by accident, the single device that would go on to define the entire technological shape of the modern world. That laboratory belonged to Bell Labs in Murray Hill, New Jersey, and the two physicists working there were named John Bardeen and Walter Brattain, operating under the supervision of a brilliant, notoriously difficult physicist named William Shockley. Their assignment sounds almost mundane compared to everything we've covered so far. Find a solid-state replacement for the bulky, unreliable, power-hungry vacuum tubes that were, at the time, the only practical way to amplify or switch electrical signals in any electronic device. They spent months experimenting with germanium, another element with the same useful semiconductor properties as silicon, trying different configurations, running into dead end after dead end. Then, on December 16, 1947, working late into the evening, Bardeen and Brattain assembled a device that looked honestly, almost laughably crude. Brattain had taken a small plastic wedge, wrapped a thin sheet of gold foil tightly around its point, and then carefully sliced a narrow gap in that foil, directly at the tip using nothing more sophisticated than a razor blade, creating two separate gold contacts sitting extremely close together, separated by just a tiny fraction of an inch. They pressed that wedge down onto a piece of germanium, applied a small electrical current to one of the two gold contacts, and discovered something remarkable. That tiny signal allowed them to control a much larger current flowing through the second contact. Amplification. A small signal in, a significantly bigger signal out, using nothing but a carefully arranged piece of semiconductor and two scraps of gold foil. They had just built the world's first working transistor, later specifically named the point contact transistor, and Brattain's original laboratory notebook from that exact evening still survives today, complete with his handwritten observations and his supervisor's official signature, witnessing the results. It's difficult to overstate how enormous this single moment turned out to be. Bardeen, Brattain, and Shockley shared the Nobel Prize in Physics in 1956 for the discovery, and the transistor itself went on to completely replace the vacuum tube across virtually every electronic device on Earth, because transistors were smaller, cheaper, far more reliable, and dramatically more energy efficient. But the truly staggering part of this story isn't the invention itself. It's what happened to that invention over the following 7 decades. In 1958 and 1959, two engineers working independently Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor both arrived separately at the idea of placing multiple transistors onto a single unified piece of semiconductor material, creating what we now call an integrated circuit, or simply a chip. This single innovation made modern electronics, in any form we'd recognize today, genuinely possible. Then, in 1965, an engineer named Gordon Moore made an observation that would come to define the entire trajectory of the technology industry for the next 60 years. He noticed that the number of transistors physically fitting onto a single chip seemed to roughly double every 2 years, driven by continuous improvements in manufacturing precision. That observation, later named Moore's Law, held up with startling consistency for decades afterward, and the results are genuinely difficult to grasp intuitively. The processor sitting inside a modern smartphone in 2026 contains somewhere in the range of 15 billion individual transistors, 15 billion tiny quantum mechanical switches packed onto a chip smaller than a postage stamp, each one operating on precisely the same basic physical principle that Bardeen and Brattain demonstrated using gold foil and a razor blade back in 1947, just unimaginably smaller, unimaginably faster, and unimaginably more numerous. Every single time you unlock your phone, send a message, or scroll through anything at all tonight, you are relying directly and completely on the exact same quantum mechanical rules we've spent this entire evening walking through together. Wave-particle duality, quantized energy levels, the Pauli exclusion principle governing how electrons stack inside silicon atoms. None of it is abstract anymore. It's sitting quietly in your pocket, running constantly, doing work you never have to think about. But transistors and classical computer chips, however dependent they are on quantum mechanical rules underneath the surface, still process information the old-fashioned way, using ordinary bits that are simply either a 0 or a 1, one state or the other, never both simultaneously. And this is exactly where the story takes its next genuinely strange turn, because a small but rapidly growing branch of physics and engineering is now trying to build something fundamentally different, machines that don't just rely on quantum mechanics happening quietly in the background, but that actively, deliberately exploit the strangest, most counterintuitive quantum behaviors directly, on purpose as the entire basis for how they compute. These are called quantum computers, and understanding exactly why they're so difficult to build, and exactly why 2026 has suddenly become such a pivotal, headline-generating year for this specific technology, means going back to a concept we spent a great deal of time on earlier tonight: superposition. The strange quantum ability for something to exist in multiple possible states at once, right up until the precise moment somebody actually measures it. An ordinary computer bit, the kind sitting inside every transistor we just talked about, can only ever be one of two things at any given moment: a 0 or a 1, off or on, nothing in between, nothing simultaneously both. That simplicity is exactly what makes classical computers so reliable. A bit is either this or that, clearly, definitely, all the time. A quantum bit, or qubit, refuses to play by that rule, thanks to superposition. A qubit can exist in a combination of both 0 and 1 at the exact same time, not as some vague uncertainty about which one it secretly is, but as a genuine, simultaneous mixture of both possibilities. Mathematically real, in exactly the same sense the wave function itself is real. And when you link multiple qubits together using entanglement, that same strange phenomenon Einstein once dismissed as spooky action at a distance. The total number of possible combinations those qubits can represent simultaneously grows explosively. 2 entangled qubits can represent 4 combinations at once. 10 qubits can represent over 1,000. 50 entangled qubits can represent more simultaneous combinations than there are stars in the observable universe. This is exactly why quantum computers hold such extraordinary theoretical promise. For certain very specific types of problems, ones involving searching through enormous numbers of possibility simultaneously, simulating complex molecules for drug discovery, or breaking certain forms of mathematical encryption, a sufficiently powerful quantum computer could, in principle, work through calculations that would take an ordinary classical supercomputer longer than the current age of the universe to complete. But there's an enormous catch buried inside that promise, and it's exactly the catch that's made building genuinely useful quantum computers so agonizingly difficult for decades. That delicate superposition, that beautiful simultaneous mixture of states, is extraordinarily fragile. The moment a qubit interacts even slightly with its surrounding environment, a stray vibration, a tiny fluctuation in temperature, a single stray photon bumping into it, that fragile superposition collapses almost instantly into an ordinary, boring, classical state, exactly one value or the other, and all the quantum advantage evaporates immediately. Physicists call this collapse decoherence, and fighting against it is, quite honestly, the single central engineering challenge of the entire field. This is precisely why most working quantum computers today operate at temperatures colder than the depths of outer space, sometimes just a few thousandths of a degree above absolute zero, sealed inside elaborate, expensive refrigeration systems called dilution refrigerators. At those almost unimaginably cold temperatures, random thermal vibrations are minimized as much as physically possible, giving those fragile quantum states a fighting chance to survive slightly longer before collapsing. Even under those extreme conditions, coherence times, the brief window during which a qubit reliably holds its delicate quantum state, are typically measured in mere microseconds, occasionally stretching into milliseconds for the very best current systems. Every single calculation a quantum computer performs has to squeeze into that impossibly narrow window before decoherence quietly ruins the entire result. This challenge is precisely why the announcement from Google in December of 2024 generated so much genuine excitement within the physics community specifically, beyond just the eye-catching headline numbers. Google's quantum chip, called Willow, didn't just demonstrate more raw qubits than previous efforts. It demonstrated something physicists consider far more significant: a working, scalable form of quantum error correction, a method for combining multiple physical qubits together into a single, more stable, logical qubit, specifically designed to actively detect and correct errors as they happen, faster than decoherence destroys the underlying information. For years, theorists had proven mathematically that quantum error correction should eventually be possible in principle, but actually demonstrating it working in physical hardware, improving as you add more qubits rather than getting progressively worse, was an entirely different, much harder challenge. Willow's results, published in the scientific journal Nature, suggested that this specific threshold had genuinely finally been crossed, That's exactly why 2026 feels like such a confusing, headline-heavy year for quantum computing specifically. Real, substantive, peer-reviewed progress is genuinely happening. At Google, at IBM, at IonQ, at multiple well-funded research labs across China and Europe, all racing toward the same distant finish line. But that genuine progress sits right alongside wildly premature claims, overhyped marketing language, and occasional, outright misunderstandings about what current quantum computers can and cannot actually do today. A functioning quantum computer capable of breaking modern encryption at scale, for instance, almost certainly still doesn't exist yet, despite what certain breathless headlines occasionally imply. Current quantum processors remain what researchers commonly call noisy intermediate-scale devices, genuinely impressive scientific achievements, but still a considerable distance away from the kind of large-scale, fully error-corrected, broadly practical quantum computer that could reliably outperform classical computers across a wide range of everyday real-world problems. And there's an idea emerging from this exact frontier of research that's genuinely strange enough to sit with as you drift towards sleep tonight. As physicists have worked harder and harder to understand entanglement well enough to actually build usable quantum computers around it, some theorists have started wondering whether entanglement might be far more fundamental to the fabric of the universe than anyone originally suspected. There's an entire emerging area of research, sometimes informally nicknamed it from qubit, seriously exploring the possibility that space and time themselves might somehow emerge directly out of networks of quantum entanglement, that the very geometry of the universe could, in some deep sense, be built out of quantum information rather than the other way around. It remains genuinely speculative, still far from settled science, but it connects directly back to everything we've spent this entire night walking through together. Superposition, entanglement, measurement, all of it possibly reaching upward from the tiniest imaginable scales to help shape the largest structure of reality itself. But quantum computing, as remarkable as it is, isn't remotely the only place where these strange rules have already quietly reshaped the world around you. There's another entire category of everyday technology built directly on quantum mechanics, one that's been running invisibly in the background of your life for decades already, and it starts with something you've almost certainly used today without ever once thinking about the century of physics quietly holding it together. That everyday technology is the laser, and the word itself is actually an acronym, standing for light amplification by stimulated emission of radiation. That specific phrase, stimulated emission, takes us all the way back to Einstein one final time, to a paper he published in 1917, years before anyone had built a working laser, decades before anyone even seriously imagined one. Einstein showed, working purely from theory, that there are actually two distinct ways an atom can release light. The first, called spontaneous emission, happens randomly whenever it happens, with no outside trigger required. The same basic process responsible for an ordinary light bulb glowing. But Einstein predicted a second, stranger possibility as well. If a photon carrying exactly the right amount of energy happens to strike an atom that's already sitting in an excited state, it can trigger that atom to release a second photon, one that's a perfect, identical copy of the first, matching its frequency, its direction, and its phase precisely. One photon goes in, two identical photons come out. Trigger that same process repeatedly in a carefully controlled chain reaction, and you get a rapidly cascading flood of perfectly identical, perfectly synchronized photons, all traveling together in the exact same direction. That is a laser. It took nearly 43 years after Einstein's original theoretical prediction before anyone actually built a working laser in a physical laboratory, which finally happened in 1960. Since then, lasers have quietly embedded themselves into nearly every corner of modern life. The barcode scanner at your grocery store uses one. Fiber optic cables, carrying nearly the entire internet's data traffic around the planet as flickering pulses of laser light, use them constantly, every second, all over the world. Corrective eye surgery uses precisely controlled lasers to reshape the cornea. Industrial manufacturing uses lasers to cut and weld metal with extraordinary precision. Every single one of these applications depends directly on a quantum mechanical process Einstein worked out purely on paper in 1917 without the slightest idea it would eventually reshape ordinary daily life on this kind of scale. There's one particular application of laser technology genuinely worth lingering on for a moment, because it represents one of the most extraordinary measurement achievements in the entire history of human science. And it happens to be quantum mechanical at its very core. It's called LIGO, short for the Laser Interferometer Gravitational Wave Observatory, and it consists of two enormous L-shaped detector facilities, one located in Hanford, Washington, the other in Livingston, Louisiana. Each individual arm of each detector stretches 4 kilometers in length. A single laser beam is carefully split into two, sent traveling down both perpendicular arms simultaneously, bounced precisely off mirrors positioned at the far ends, and then recombined back together at the starting point. If a gravitational wave happens to pass through the detector, an actual ripple traveling through the fabric of space-time itself, typically triggered by something as violently dramatic as two black holes colliding somewhere unimaginably far away. It stretches and compresses space by an unbelievably tiny amount as it passes through Earth. LIGO is engineered to detect a change in the length of its 4-kilometer arms smaller than 1/10,000th the width of a single proton, a level of precision that only becomes physically achievable because of quantum mechanical properties of the laser light itself and because of specialized quantum techniques engineers use specifically to reduce quantum noise interfering with the measurement. When LIGO detected its first confirmed gravitational wave in September of 2015, generated by two black holes colliding roughly 1.3 billion years ago, it wasn't simply confirming a prediction Einstein had made about general relativity a full century earlier. It was also, quietly, a genuine triumph of quantum engineering built directly on stimulated emission, the exact same phenomenon Einstein had theoretically predicted in that same extraordinary stretch of his career. And there's a particularly satisfying irony worth pausing on here before we continue. The same man who spent decades of his life arguing passionately against the probabilistic, uncertain nature of quantum mechanics also personally, directly laid the theoretical groundwork for one of quantum physics' most spectacularly successful practical technologies. Einstein never fully made peace with quantum theory's stranger philosophical implications, but the underlying physics itself, the actual equations, the actual predictions, turned out to be reliable enough that engineers could build genuinely extraordinary things directly on top of it, whether or not Einstein personally felt comfortable with what those equations seemed to be saying about the fundamental nature of reality. There's one more everyday technology worth mentioning before we start winding this whole story down for the night, because it quietly demonstrates just how deeply interconnected quantum mechanics and Einstein's relativity have become in practice, working together seamlessly, even though the two theories still haven't been fully unified into one single, complete framework by physicists even today. Every GPS satellite orbiting overhead carries an extremely precise atomic clock on board, one that keeps time by measuring the specific, reliable frequency at which electrons inside certain atoms transition between distinct quantum energy levels, the exact same basic phenomenon we spent so much time examining earlier tonight when discussing Bohr's atomic model. But those satellites also travel at significant speed relative to the surface of the Earth, and they sit considerably farther away from Earth's gravitational pull than we do down here on the ground. According to Einstein's theory of relativity, both of those factors cause time itself to tick at a very slightly different rate up in orbit compared to time passing down here at sea level. If engineers simply ignored these relativistic effects entirely, GPS positioning would drift by roughly 10 kilometers every single day, rendering the entire system essentially useless within hours. So every GPS satellite has its onboard atomic clock deliberately, precisely adjusted before launch, running very slightly slower than an identical clock would run down on Earth's surface, specifically calibrated to compensate for the relativistic effects it will experience once safely in orbit. Quantum mechanics provides the extraordinarily precise clock. Relativity tells engineers exactly how to correct that clock, and the practical result of combining both theories together seamlessly is that you can pull out your phone tonight and locate the nearest coffee shop tomorrow morning to within just a few meters of accuracy. That's the actual, tangible, physical world running quietly on top of physics that once seemed like nothing more than pure, abstract, dinner table argument between Einstein and Bohr in the 1920s. And having walked through the entire arc together now, from a glowing piece of metal in a 19th century laboratory, all the way to satellites correcting for the bending of time itself, in orbit above your head right now, it's worth stepping back one final time and asking honestly just how much of any of this we, collectively, as a species, actually understand. Here's the honest, slightly humbling answer to that question. More than a century after Max Planck reluctantly introduced the idea of quantized energy purely as a mathematical trick he privately hoped would eventually be replaced by something more sensible, physicists still don't agree on what quantum mechanics actually means at its deepest level. Not because the theory doesn't work. It works extraordinarily well, better than any other theory human beings have ever constructed. The disagreement isn't about the equations. It's about what the equations are actually telling us about reality itself. Underneath all the successful predictions, the Copenhagen interpretation, the one championed by Bohr and Heisenberg, and the one that most working physicists default to, without necessarily thinking too hard about its philosophical implications, still holds that a quantum system genuinely doesn't have a definite state until measurement forces one to appear, and that asking what's really happening in between measurements simply isn't a meaningful question to ask. But Copenhagen isn't the only serious interpretation still standing today. Not by a wide margin. There's the many worlds interpretation, first proposed by a physicist named Hugh Everett in 1957, which takes a genuinely startling approach to the entire measurement problem. Instead of saying, a wave function collapses down to one single outcome the moment you measure it, Everett proposed that every possible outcome actually happens, each one branching off into its own separate, equally real universe. Under this view, when you measure an electron and find it spinning clockwise, there's an entire parallel version of you, in an entire parallel version of the universe, who measured the exact same electron and found it spinning counterclockwise instead. And neither version of you ever finds out about the other. It sounds like science fiction. A genuine, still active minority of serious physicists take it completely seriously as an actual physical description of reality, precisely because it lets you keep the mathematics of quantum mechanics perfectly intact without ever needing to invoke a mysterious, poorly defined collapse at all. There's also the pilot wave theory, sometimes called Bohmian mechanics, originally developed by de Broglie himself and later revived and expanded by the physicist David Bohm in the 1950s. This approach actually does bring back something very close to Einstein's original hope: hidden variables, particles that genuinely do have definite positions at all times, guided along by an underlying wave that pushes them deterministically from place to place. It reproduces every single experimental prediction of standard quantum mechanics perfectly, without ever needing pure randomness at its foundation. The cost is that it requires accepting a strange, distinctly non-local form of instantaneous influence connecting distant particles together. Exactly the kind of thing Einstein originally found so deeply objectionable, and there are others still. Relational quantum mechanics, which suggests that a quantum system's properties are only ever meaningful relative to whatever else is observing or interacting with it, and QBism, short for quantum Bayesianism, which treats the wave function not as a description of reality itself at all, but purely as a reflection of one specific observer's personal, evolving beliefs about what they expect to happen next. Smart, serious, deeply knowledgeable people genuinely disagree passionately about which of these pictures, if any, actually describes what's happening underneath quantum mechanics. And here's the part that tends to surprise people the first time they really sit with it. This disagreement doesn't actually slow anything down in practice. Every single piece of technology we walk through tonight, transistors, lasers, GPS satellites, quantum computers, works exactly the same way, regardless of which interpretation you personally find most convincing. Engineers building quantum computers in laboratories right now don't need to resolve a century-old philosophical dispute before their machines will function correctly. The math simply works, reliably, precisely, whether or not anyone fully agrees on what that math is secretly describing about the fundamental nature of reality. Consider, for just a moment, how strange that actually is. Quantum electrodynamics, the specific branch of quantum theory describing how light and matter interact, predicts the magnetic properties of a single electron to an accuracy of roughly 1 part in 10 trillion. To put that number in some kind of tangible perspective, that's a level of precision comparable to measuring the distance between New York and Los Angeles, down to within the width of a single human hair. No other theory in the entire history of science has ever come close to matching that kind of precision, verified over and over again in laboratory after laboratory for the better part of a century now. So we find ourselves in a genuinely strange, almost paradoxical position. We know how to use quantum mechanics with staggering, unprecedented precision. We build phones, satellites, lasers, and increasingly powerful quantum computers directly on top of it, all of it working exactly as predicted every single time. And yet we still don't have complete agreement on what it actually means, on what's truly happening to a photon or an electron in the silent gap between one measurement and the next. Perhaps that's simply the honest, humble state of human knowledge on this particular subject, at least for now. We've learned to work the machinery with extraordinary skill long before fully understanding every gear turning quietly underneath it. There's something genuinely comforting hidden inside that uncertainty if you let yourself sit with it for a moment rather than fighting against it. An entire century of the most brilliant human minds who ever lived, people like Planck, Einstein, Bohr, Heisenberg, Schrödinger, and Bell, spent their careers wrestling with confusion this deep, this genuinely fundamental, and they didn't always resolve it either. Sometimes they were simply wrong, occasionally brilliant, and remarkably often willing to change their minds when the evidence eventually demanded it of them. If the ideas we've covered tonight still feel a little slippery in your own mind right now, a little hard to hold on to firmly, you're in exactly the same position the greatest scientific minds in human history found themselves in as well. That's not a failure on your part. It's simply what genuinely grappling with the deepest, strangest layer of physical reality has always felt like for absolutely everyone who has ever seriously tried. So here we are at the end of a story that started with a piece of glowing metal in a 19th century forge and somehow wound its way through gold foil experiments, an aristocrat's strange question about waves, a hay fever retreat on a windswept island, a scandalous holiday in the Swiss Alps, breakfast arguments in Brussels that lasted for decades and finally landed here, tonight, in 2026, inside the phone charging near your bed and the satellite quietly correcting itself in orbit somewhere far above your roof. Think back for just a moment over everything that had to happen for this exact night to unfold the way it has. A cautious, traditional man who didn't want to be a revolutionary had to get desperate enough to introduce an idea he privately hoped was wrong. A bored patent clerk had to spend his lunch breaks thinking about light instead of finishing his paperwork. A quiet, slow-speaking Dane had to be audacious enough to simply declare that classical physics didn't apply anymore without knowing why. A French prince had to abandon history for physics because of dinner-table conversations with his brother. A young man suffering from allergies had to escape to a barren island just to think clearly. An older physicist had to sneak away to the mountains with someone who wasn't his wife. And after all of that, the single greatest scientific mind of the 20th century had to spend the last 3 decades of his life constructing brilliant argument after brilliant argument against a theory that, in the end, turned out to be right anyway. None of these people set out to build the device sitting somewhere near you right now. None of them could have possibly imagined a supercomputer, small enough to fit in a pocket, an eye surgery performed with light, a satellite correcting for the bending of time itself. They were simply trying to understand why hot metal glows the way it does, why atoms don't instantly destroy themselves, why light seems to be two contradictory things at once. They were following small, stubborn, uncomfortable puzzles, wherever those puzzles happened to lead, one confusing step at a time, often not believing their own results, often hoping someone else would eventually prove them wrong. And here's the part worth carrying with you as your eyes get heavier. Every single confusing thing we walked through tonight, the ultraviolet catastrophe, wave-particle duality, the impossible stability of the atom, Bohr's unexplained orbits, de Broglie's strange matter waves, Heisenberg's uncertainty, Schrödinger's spreading wave function, Einstein's spooky entanglement, Bell's decisive experimental verdict, all of it eventually stopped being confusing enough to stop physicists cold. It got absorbed slowly, patiently, into an actual, working, reliable picture of reality. Confusion wasn't the enemy of understanding in this story. It was the very first step of it, every single time. That's genuinely worth remembering the next time some headline about quantum computers or quantum encryption crosses your feed and makes your head spin a little. The confusion you're feeling isn't a sign that you're missing something everyone else already understands. It's the same confusion that sat, unresolved, in the minds of Planck and Einstein and Bohr and Heisenberg, sometimes for years, sometimes for entire careers. They didn't get comfortable with these ideas quickly either. Nobody does. That discomfort is simply what it feels like to stand close to something gently strange and true. We are, all of us, walking around inside a universe built on rules that don't care whether they make intuitive sense to a species that evolved to track animals across open grassland. Energy comes in indivisible pieces. Particles are also waves. Nothing has a definite position until something forces the question. Two particles, separated by the entire width of the galaxy, can be linked together so completely that measuring one instantly determines the other. And somehow, out of all of that genuine strangeness, we've managed to build lasers and phones and satellites and machines cold enough to make quantum computers briefly, fragilely work. The strangeness didn't get in the way of the engineering. The strangeness became the engineering. You've been lying here this whole time, in the dark, while trillions of photons and neutrinos moved silently around and through you, while the electrons in every atom of your body obeyed rules discovered by people who spent their entire lives arguing about what those rules actually meant. None of that machinery needs your understanding to keep running smoothly. It was running long before Max Planck ever sat down at his desk in Berlin, and it'll keep running long after tonight is over. Whether or not you remember a single name we mentioned by the time morning comes. So let all of it go now. Let Planck's reluctant quanta go. Let Einstein's stubborn arguments go. Let Bohr's strange, unexplained orbits go. You don't have to hold on to any of it tightly. You don't have to fully understand the difference between Copenhagen and many worlds, or remember exactly how a transistor works, or carry any of tonight's confusion forward into tomorrow. The ideas will still be here whenever you want them again, patient and unchanged, the same way they waited quietly for over a century before anyone figured out how to use them. Let your thoughts get looser now. Let them stop trying to force everything into neat, tidy boxes, the same way the universe itself never quite fit into the neat boxes physicists originally built for it. Somewhere in your own mind right now, countless quantum mechanical processes are already humming along quietly inside your neurons, doing the work they always do, without needing your permission or your attention. Let them keep doing that work. Let the uncertainty be all right. Let the not quite knowing feel restful, instead of unsettling, the same way it eventually did for the very physicists who discovered all of this in the first place. And let all of it gently, reliably carry you into sleep.